So I left you yesterday with a small little exercise, and that little exercise was to work through these questions here, just to get into your heads the basics of what we spoke about yesterday. So just to go through these very quickly, a hydrogen atom that has lost an electron is simply a bare, answer, proton. And please remember too, bare protons don't exist in Earth. They don't just float around in space. They have to be part of something. All right. A soluble base is called. Now, I didn't mention this in the slides yesterday, but it's something that we would have mentioned in relation to junior cert chemistry. When a base is soluble, it's called an alkali. Okay. And an alkali is just a class of base that dissolves in water. Just keep that in mind. Write down the Arrhenius definition of a base. Now, a base, it's a very simple definition. The Bronsted-Lowry ones are quite short, but the Arrhenius one's a little bit longer. And Arrhenius simply said that a base is any substance that produces OH minus ions in solution. That's the Arrhenius definition of a base. Another name for the hydronium ion is the hydrogen ion. Hydrogen, Hydrogen, because if you remember, we had H3O plus, and H3O plus is nothing more than H2O, which is neutral, carrying on its back a H plus. So we can kind of say, yeah, H plus, the hydrogen ion, is what we use in terms of the symbol nowadays, but it is part of something far greater. It's part of the H3O plus hydronium ion. The Bronsted-Lowry definition of an acid is, well, Bronsted-Lowry has got to do with the proton moving from one to the other, and the acid is a proton donor, and that's extremely important. It's a proton donor. Give two reasons why Bronsted-Lowry theory is more satisfactory. Now, we talked about this yesterday. Bronsted-Lowry number one allows other solvents to be classified as producing acidic and basic effects when things are poured into them, okay? And secondly, it also then does away with the fact, as Arrhenius said, that they had to be acids in water and they had to be bases in water. That's not the case. We now know, thanks to Bronsted-Lowry, that you can have acid and bases in gaseous form. Okay, because Arrhenius was all taken up with, oh, when you put this into water, it produces H+. When you put that into water, it produces OH-. Bronsted-Lowry theory simply says, no, an acid is anything that donates a proton, whether it's in water or outside water, and likewise a base is anything that receives a proton, whether it's inside water or outside water. And in fact, Bronsted-Lowry even said it doesn't have to be water. It could be alcohol, it could be cyclohexane, it can be any other solvent. That's key. Part G, why are bases such as sodium hydroxide often used in oven cleaners? Now, I gave you a hint yesterday. Bases have a soapy feel, okay? And the reason why bases have a soapy feel is because the lipids on the surface of your skin, okay, the oils that are on the surface of your skin, our skin is always oily, that's a lipid. So those lipids, when they react with the base, are transformed straight away into soap. So therefore, bases have a very good way of attacking lipids and removing them for where we don't want them to be. So they can bond with the lipid and pull the lipid into water. And all bases can do that, okay? So when you're talking about oven cleaners containing a base, it's because they're able to react with the lipid and pull that lipid into water away from the item that you wish to clean. Part H, distinguish between a weak base as defined by the Arrhenius theory and a Bronsted-Lowry theory. Now, we've got four words in chemistry we've got to be very careful of. Concentrated, dilute, weak, and strong. Okay? Concentrated and dilute has to do with the amount of water. Full stop. Okay? But weak and strong has to do with the production of H+. So therefore, if we're talking about a weak base, we're talking about bad production of OH minus, because don't forget it's Arrhenius' theory, so we have to make reference to the OH minus. So distinguish between a weak base as defined by Arrhenius' theory and the Bronsted-Lowry theory. Well, first of all, a weak base in Arrhenius' theory is something that produces little OH minus in water. Excuse the handwriting now. And what does Bronsted-Lowry say? Well, a base that's weak is a bad proton acceptor. It doesn't accept protons very well. So therefore it's a bad proton acceptor. because all bases, don't forget, in Bronsted-Lowry theory are proton acceptors. Okay, so that's Bronsted-Lowry theory. How does part I? How does the Bronsted-Lowry theory define a strong acid? A strong acid in Bronsted-Lowry, make reference to the proton. It's a good proton donor. That's all you've got to remember. A good proton donor. That's all you got to say. And then an amphoteric substance is. Now, water is the only one that we've studied so far. Water under Bronsted-Lowry theory can donate protons and can also receive protons. So therefore an amphoteric substance is any substance that can act as an acid or a base. Okay, and water is generally the example that's used under Bronsted-Lowry theory. So I hope they're okay. If you have any questions on those, you can come back to me with an email if you need any further clarification. We've got to move on to the next part. So I want to talk about what we call a reversible reaction. Now, a reversible reaction, as you notice by the arrow here, is one that goes both forward and then goes back. Okay, you might say, how the hell does that happen? Well, first of all, we start off with these two. Okay, so we start with these two substances here and we put them together. These two substances begin to produce these two, HCO3 minus and H3O plus. But as soon as these two pick up in concentration, they begin to collide with one another. Because don't forget what a chemical reaction is. A chemical reaction is nothing more than the collision of particles. Okay, so as soon as their concentrations pick up, they start to collide with one another. And then they undo the process. They go back to where they were at the start. Then they collide and they go forward. Then they collide and go back. So you've got this kind of a cyclic process going on within this particular system. All right. So that reversible reaction simply means that in the one chemical equation, there are two systems. The forward one giving rise to a concentration of HCO3 minus and H3O plus, and a backward one which is giving rise to the increase in concentration of H2CO3 and H2O. Now next year, roughly around this time next year, we'll be looking at this particular reversible phenomenon in detail in terms of mathematically measuring where the actual balance is. But don't worry about that for this year. That's enough for now. So that's what a reversible reaction is. One that starts off with 2, A plus B, gives C plus D, but as we increase the concentrations of C plus D, they continue to collide and they give back A plus B. Okay, so you've got this kind of a, what we call a cyclical process within that given system. This reaction is shown by the double arrows. Now, the double arrows are extremely important, and they're only half-headed arrows, you know, just like that, that's all. Half-headed arrows of the same length. And that's key, because once they're the same length, that means the forward and backward reactions are occurring at the same rate. That's important, okay? If I was to do something like that, silly, then I'd be saying that the reaction going forward is occurring at a far greater rate than the one going backwards. So just be careful that you make sure your arrows in the middle are of exactly the same length. So can we work out in this one who's receiving the proton and who's donating the proton? But this time I want you to tell me in the reverse reaction, okay, the one that's going backwards. Now let's think for a moment, because in order to work out what's going on going back, we've got to work out what's going forward first, okay? So HCO3 plus H2O, what happens? The H2O has become H3O plus. So the H2O has picked up a proton from the carbonic acid. So there's the transfer, okay? Now, if the transfer going forward is from the carbonic acid to the water, well then obviously the transfer going back is the water handing back the proton. So in other words, in the backward reaction, the proton is sent the other way. So now, going forward, we have what's called the acid and the base. But going backward, we have what's called the conjugate acid and the conjugate base. Now they're extremely important terms, and conjugate is always the prefix that we use, the word we use when we're dealing with the reverse reaction. Okay, going forward, it's the acid and the base. Excuse me. Going backward, it's the conjugate acid and the conjugate base. So can I work out who's donating and who's accepting the proton here going backwards? I can. Because the water molecule picked up a proton going forward, well then going backward, it's going to give back that proton. So going backwards, the H3O, the hydronium ion, is going to donate back a proton to the HCO3 minus, meaning that this one will be under Bronsted-Lowry theory the carbonic acid, jeepers, the conjugate acid, and the HCO3 minus will be the conjugate base. Okay. In the reverse reaction, as we said already, the HCO3 minus now accepts a proton from the H3O plus. So in other words, it's quite easy. See what happens going forward and just undo the process going back. So if the water accepts going forward, the water will donate and give back the proton going backwards. H3O therefore acts as what we call the conjugate acid, and HCO3 acts as a conjugate base in the reverse reaction. And that's extremely important. Okay, so there's the reaction with the proper terms given. Now, one thing I want to point out here is this. H2CO3 has become HCO3 minus in the forward reaction, and H2O has become H3O plus in the forward reaction. Now I want you to look at the terms below the two things I've just linked. The acid going forward is linked to the conjugate base going backwards, and the base going forward is linked to the conjugate acid. So in other words, what I can say here is that if the system is reversible, then the species on either side are linked through conjugation. The acid going forward is linked to the conjugate base, and the base going forward is linked to the conjugate acid. Now, why is that important? It's important because, if you notice, H2CO3 becomes HCO3 minus. H2O becomes H3O plus. And if you were to look at both of those species very, very carefully, you'd notice, hold on a second, the only difference between the acid and the conjugate base is the removal of a proton, and the difference between the base and the conjugate acid is the addition of a proton. So therefore, what we're beginning to see here is that the acid and the conjugate base only differ from one another by a single H plus, and the base and the conjugate acid only differ from one another by a single H plus. So therefore, we've got a definition. A conjugate pair of substances, or a species, whatever you want to call them, is a pair of substances that differ from one another by a single proton. That's it. So a conjugate acid-base pair are a pair of substances that differ by a single proton. So if you've got a species on the left-hand side and on the right-hand side, and the only difference between them is H+, they are what we would call a conjugate acid-base pair. Okay, so keep that in your head going forward. Now, take a look at this one here. That's the same reaction, but look at the way I've broken it down. In the forward reaction, the acid is H2CO3 and the base is H2O, because the proton is being donated from the acid to the base under Bronsted-Lowry theory. And in the reverse reaction, we notice that the H3O plus is going to donate back to HCO3 minus, the proton it took in the first place, making H3O plus the conjugate acid and HCO3 minus the conjugate base. So, as I told you already, a conjugate acid-base pair is any pair of substances that differ by a single proton. So if the only difference between the two molecules is H+, then you have located what we would call a conjugate acid-base pair. So here's an example. Ammonia with water sets up what we would call a reversible system with NH4+ and OH-. Now, first of all, let's take Bronsted-Lowry theory and apply it to see who the acid and the base is going forward. We notice that the water was H2O, but the water has now become OH-. So in other words, one of these H's has been given to the ammonia, making that the acid, as I already have underneath it, and this one here the base. So if the water donates a proton going forward, then it's going to be that way of a donation on the way back. The NH4+, the ammonium ion, will redonate back what it took going forward to the OH-. Now what does that mean? This is your conjugate acid and this is your conjugate base. Now, where are my conjugate acid base pairs? Watch carefully. The NH3 and the NH4+ differ from one another by a single proton. So they are what we would call a conjugate acid-base pair. And likewise, the H2O and the OH- differ from one another by H+. So the H2O and the OH- are also another conjugate acid-base pair. So in this reaction, there are two conjugate acid-base pairs. There's this one here, the base with the conjugate acid, and this one here, the acid with the conjugate base. Okay, so quite easy for us to find out which one they are. So let's take a look at this one. I'm just going to do the last one here because you can do the rest yourselves. I'm going to take this one here. Let's see if we can work out what the conjugate acid-base pairs are in all of these reactions. Let's take the last one. H2SO4 and HNO3 react to give H2NO3 and HSO4 minus. Now, what's happened? Take a look at this carefully. The HSO4 minus started off as H2SO4. So therefore we notice that the H2SO4 has lost a proton, meaning that it has donated this way. So that's the acid and that's the base. Likewise here, what do we notice? The H2NO3 plus that received the proton going forward is the one that can redonate back to the HSO4 minus going backwards. So therefore this is the conjugate acid and this is the conjugate base. Now what are the conjugate acid base pairs? Well, the H2SO4 is one part of the conjugate acid base pair with this one. So H2SO4 and HSO4 minus are an acid base conjugate pair, and likewise HNO3 and H2NO3 are a conjugate acid base pair in the same reaction. Okay, so would you just try it there with this one, and this one. Pause it, pause the video now, just take those three, don't worry about the top one, that's just a general reaction. If you want to try top one, do, fine. Try those four, pause the video now, try them, see if you can work out where the acid base, conjugate base are, and then the two conjugate acid base pairs in each of those reactions. Okay, a typical question they ask in the leaving cert is something like this. They'll focus on one species and they'll say, what's the conjugate acid or the conjugate base of HC2O4 minus? Now here's what I need you to think of. What is the conjugate acid? So in other words, I want to work out what the conjugate acid is, meaning that I must be starting off with the other half of that pair, which is the base. Okay, so if I want to work out what the conjugate acid is, then my starting point must be a base, HC2O4 minus. Now, what do bases do? Bases under Bronsted-Lowry theory accept protons. So that means that if this accepts a proton, it goes to H2C2O4. And because it's accepting a H plus, notice what happens. The H brings that H up to 2, and the plus and the minus cancel. So there's your conjugate acid. Okay. Next question says, what is the conjugate base of HC2O4 minus? Now, if I want to go to the conjugate base, that means my starting point is an acid. All right. And the starting point, again, is the same, HC2O4 2 minus. Now, under Bronsted-Lowry theory, what do acids do? They donate H pluses, meaning I've got to take a H plus away from this. So not only am I going to remove the H, leaving C2O4, I'm also removing another positive, which will bring me down to 3 minus. Okay, and that is the conjugate base of HC2O4. Notice that's going to be the starting point for both. If they're asking you to find the conjugate acid, then this will be starting off as a base under Bronsted-Lowry theory, to which you will add a proton. If you're looking for the conjugate base of HC2O4 minus, then this will start off as a base, sorry, as an acid, and then you will add a proton in order to work out the conjugate base. Okay, and that's written there as far as I know. So H2CO4 is a base. So we start off, if they're asking what's the conjugate acid, this becomes a base. And bases under Bronsted-Lowry theory accept protons. So you add on a H plus to get to conjugate acid. And likewise, if you're looking for the conjugate base, you start off with an acid, which you remove a H plus from to give you HC2O4 minus, becoming C2O4 2 minus. I think I said 3 minus in the last one, didn't I? A bit silly. Anyway, it's gone. Okay, here's your job. On this page and on this page, yeah, I want you to take this, I want you to pause this one now, and I want you to write down the conjugate base of each of the following. Now remember, if you're looking for the conjugate base, All of these are starting off as acids. So what do acids do under Bronsted-Lowry theory? Okay, keep that in mind. That's the first one. So you can pause that now and go ahead on those. And when you're finished these, you can go on to this one. Write down the conjugate acid. And if I'm being asked for the conjugate acid, that means I'm starting off with a base. And under Bronsted-Lowry theory, ask yourself, what do bases do? Okay. So pause, go over those two, finish them, and I'll give you the solutions in the next class. Okay, so just to finish this off, indicate which species are acting as acids and which are acting as bases in the following reaction, and then indicate also the conjugate acid-base pairs. Lovely leaving cert question, and this comes up fairly regularly. Okay, and all we've got to do is inspect. HNO3 added to H2F2 is reversible with H2NO3 plus and HF2 minus. Now what's happened? Well, first of all, we notice that what was H2F2 has become HF2. So there seems to be a movement of a proton this way, meaning that's the acid and that's the base in the forward reaction. Okay, now going backwards, let's take these two. Because the H2F2 has lost one and donated it over here, the only thing that can happen going back is that the H2NO3 plus, which has now got the extra proton, will simply give it back, meaning that's the conjugate acid and that's the conjugate base. And where are the pairs? Indicate also the conjugate acid-base pairs. Here's the quickest way to do it. Just link the base with the conjugate acid and call it number 1, and then link the acid with the conjugate base and call it number 2. That's it. So you've got your acid, your base, your conjugate acid, your conjugate base, and your conjugate acid-base pairs. And notice, please, that the base and the conjugate acid only differ by a H+, and the H2F2 and the HF2 minus only differ by a single proton, a H+. So that's how you do those questions. Now, you're not getting away with just doing those little bits beforehand. You've got more work to do here. Acid, base, acid, conjugate base, and then you've got your conjugate acid-base pairs as follows. That's the best way to write down the answer. Just fill in the letters and then put the arrows in to link the two species on either side that differ by a single proton. Okay, you're going to do the same with these. All right, now I want you to do them all because you do need to practice these things. But I want you to do exactly the same thing as I did in the previous one. Take each equation, work out the acid and the base. That one's already done for you on the previous slide. Okay, but take each of these equations, work out in the forward reaction where the proton is going, work out in the backward reaction how the proton is going to be returned, label the acid, label the base, label the conjugate acid, label the conjugate base, and then join the pairs by arrows. Okay, so you can work away on those plus the two questions before that, and once that's finished, then we will come back with the next section.